Welcome back to the lecture series in animal physiology. So we are into the 10th week and we have finished 2 lectures where I have talked about the basic architecture of the heart, and then we talked about the 2 basic systems, the contraction system and the conduction system, and post that we talked about the conduction system, or rather that electrical component of the heart which regulates the contraction process, which thereby leads to the mechanical action of the filling and unfilling of the different chambers, which includes your 2 upper chambers and the 2 lower chambers. So in the previous class, if you recollect, we talk about the circuit which spans between SA node, the sinoarterial node, all the way to the AV node, and in that process the distance traversed, the circuit is kind of bifurcated and into 2 like this, and it merges at one point. And you must have observed that the distance between SA node to AV node is lesser when the circuit is passing through the right upper chamber as compared to when the circuit passes through the left upper chamber. So that brings us the first clue that electrical activity is observed in the right upper chamber as the first one, followed by the left upper chamber, then followed by the right lower chamber, right ventricle, and followed by the left ventricle, right. So the sequence of event: right atrium, left atrium, right ventricle, left ventricle, A, B, C, D. And then we talked about how these events are kind of, staggered over one another. This kind of a set, that one set, top of that another set, there is a third set, there is a fourth set, and there are zones of, in a Venn diagram of sets, you will see zones of where 2 events happen at the same time, partly, not fully. Say for example, an event start at T0 to T5. So the second event must have started at around say T2. So between T2 and T5, and that may last beyond T5, it may last for say T7, okay. But between T2 to T5, it has both the events are occurring, okay. And similarly, a third event may have started at T4. So it means that the third event is kind of staggered with the second event. Similarly, the fourth event at the later phase may be staggered along with the third event. Like then we talked about the action potentials which are generated by the conduction systems, which are the pacemaker cells. Now I told you the pacemaker cells follow a spontaneous activity, electrical activity, where they shoot action potential while sitting at -40 millivolt. Interestingly, the most critical point what I wish to highlight, which will help you to deviate out from the traditional action potential, is that all the action potentials starts from -80 or -70 millivolts. Those follow the first step, which starts from -70 or -80, is by activation of the fast acting voltage gated current or voltage gated channel, and these are sodium channels. This what initiates the first straight line what you see of going up overshooting 0 is because of the entry, sudden entry, or a very narrow window of entry of the sodium ions inside the cell, followed of course by outflow of the potassium, and again the homeostasis is being maintained by using a channel which throws the sodium channel out of the cell, whereas it regains the potassium channel from outside. So this is how an action potential in a standard neuron performs. Whereas in the pacemaker cells, these special fast acting voltage activated sodium currents are missing. So if you remember, when I talked about the action potential, I told you there are variants of action potentials. Action potential does not necessarily, mark my word, does not necessarily meant that it can only be initiated by these voltage gated, fast acting voltage gated sodium channels, which lead to the sodium current. Of course, that's why I'm kind of, whenever I talk about channel, the current word kind of pops up. So these pacemaker channels or pacemaker cells are governed by a very specific kind of calcium channels. There is a role of sodium channel, but not as prominent as could be as observed in the neurons or even cardiac myocyte, which will be coming just post this, because there are three things what has to be very clearly told today, and I am ensuring that this class will give you a feel about the variation, at least the broad variation of action potentials which are existing. So the second type, what we talk about, the pacemaker cells, they follow an action potential which is starting at -40 and spontaneously going to overshooting 0 and coming back, overshooting 0 coming back, overshooting 0 coming back. This is how the pacemaker cells work. Now, I told you when I showed you the diagram of the heart, you remember, I told you it's a very small fragment. It's kind of in a small room that you see a kind of a wire which is moving. So that's what from SA to AV to bundle of E's to Purkinje fiber. This is a very small amount. Now, what these pacemaker cells does, so this is one part where I'll give you the notes. Notes are not really important here. What is important is the concept. Try to understand the concept, and that's why I'm not drawing anything. I'm trying to converse with you about the basic fundamental concept. So say for example, if I consider this as the part of the conduction system. So this is some kind of conduction going on. Now, or say for example, this is a better example. Okay, I consider this wire as part of the conduction system. Okay, so this is where from SA node it is going to the AV node and splitting up likewise. Now, surrounding, imagine there are cells. So what will happen when the current will flow across this wire? It will create a kind of induction in and around it, which most of you know, like when a conductor is moving, it creates a magnetic field, and likewise so on and so forth. This basic fundamental you all have studied, right? Now, it will create a kind of an induction effect around it, and thereby what it will do is, and this is happening spontaneously, right? I told you that this whole thing is the pacemaker cells which are there. It will create an inductive effect around the cells around it, and these cells which are surrounding it are called cardiac myocytes. These are the cells around it, not this black colored wire. This black color wire is your SA to AV to bundle of His to Purkinje fibers. In and around it there is an induction effect which happens, and that induction effect leads to the activation of the cardiac myocytes which are surrounding it. Is it making sense? So now I'll just draw the first diagram for you to understand. Say for example, so let's keep this diagram simple. Instead of, so if this is the four chambers of the heart, okay, right upper, left upper, right lower, left lower, and we have already seen that this is how the pacemaker circuit is. AV, SA, right? And of course, for those who wants to visualize it in a real life, it is something like this. where you have the heart in 4 chambers. I'm splitting it up, and here you have the SA node, here you have the AV node. This is traveling like this, this is traveling like this, this is traveling like this, this is traveling like this. In a real life, if you want to really visualize how this system really looks like, right? Now, here is your AV and here is your SA. Fair enough? Now, what is important is, so once again, okay. Now, what is important here is something that while the current wave is moving, it is creating an induction effect in the surrounding, which I am showing by the cardiac myocytes, which are constituting this whole chamber. This chamber is made up of cells. It's kind of a sac, okay, and this sac is made up of the cells which are called cardiac myocyte cells, whereas these are made up of pacemaker cells, and these are the cardiomyocyte cells. And cardiomyocyte cells, okay, here I will add one more thing for your understanding. Heart is made up of at least 4 to 5 different kind of cell types or tissues. The one which I have already talked to you about is a very small percentage, very small percentage, less than 10%, maybe less than 5% even could be, is the pacemaker cells, one, which constitute the conduction system. So, pacemaker cell constituting conduction system, okay, 1. Then you have cardiac myocyte, which is constituting the contraction system. Apart from it, you have 2 other important things which are forming endothelial cells, forming the blood vessels. You remember that when we talked about superior vena cava, inferior vena cava, aorta, and these are all blood vessels. So, these are very thick vessels which have endothelial tissue which is making them, they have a different kind of stretch, strain, curves and their flexibility. So, and then on top of that you have a series of stem cells which are sitting there. There is a lot of research going on to convert some of these stem cells to cardiac myocytes. And apart from it, there is another cell type which is forming these different kind of valves, which are more cartilaginous tissue kind of a stuff, okay, much different kind of soft tissues. So, all in all you can see almost, so if I number them in terms of their intensity, so you have cardiomyocyte type 1, then endothelial cell, you have conduction system, this is pacemaker cells, then you have these valves, what's made up of, and 5. So, that is why I was telling you, at least prominently known 4 to 5 different kinds of cells which constitutes the heart. Now, coming back. So, these sacs, the right upper chamber, left upper chamber, right lower chamber, left lower chamber, these sacs are made up of cardiomyocytes, and these sacs expansion, contraction is regulated by the conduction circuit, right. So, whenever there is a current stream flowing through this conduction circuit in the form of ionic currents. So, this is one more thing. So, if you look at the conduction system, it is something like this, okay. So, essentially these are the cells which are sitting there in a 3 dimension. Like this. Okay. Lot more cells here. These are the hubs. Now when the action potential is generated, so it's a spontaneous action potential, it travels like this. So it gets generated at this point spontaneously, and it travels in two different directions. I am following the circuit exactly the time window, how it kind of moves on, right. So coming here, moving like this, coming here, moving like this. Okay. So this is how the current impulse is moving, and while this is moving, it is creating a, as I was telling you, it is creating an induction effect in the surrounding, and this induction effect is transferred to the cardiac myocytes. So from conduction system, it moves on to the contraction system. So whatever changes which are happening there. Now because of this induction effect, the contraction system, which constitute the cardiac myocytes, so what happen is, if these are the conduction system, this leads to an induction effect. Okay, before I draw it like that, let me put the, okay. So this is, these cells are in terms of the millivolt are sitting at minus 40 millivolt, and they are overshooting 0 here. Now these are pacemakers. Now pacemaker has this induction effect which activates cardiomyocytes, and in the cardiomyocytes, again let me put the scale. So they are sitting at minus 80 millivolt. Cardiomyocytes are sitting at minus 80 millivolt. Now from there, the cardiomyocytes, because of that induction effect, shoots an action potential like this. Actually, if you follow me, the second there is a gap I have shown, it is actually, it should be like this. Okay. So if you look at the shape of the action potential and from what resting membrane potential is picking up, it will give you a very clear idea about at what resting membrane potential a cell will set, so that it can shoot an action potential spontaneously. So the pacemaker are spontaneous action potential generators. These activates the cardiomyocytes, which generates the action potentials in cardiomyocytes. Now the cardiomyocytes, if you look at, now I will just, as a comparison, I will put, when you see a neuronal neuronal action potential, you must have seen it like this, right? Now look at the difference in the action potentials. Forget about the peak it is taking up. This part, do not worry about it. I mean, I can always bring down the peak like this. Okay. The important part is this part. Look at the plateau which it is taking, whereas no such plateau is being observed neither here nor in the neuronal ones, but cardiomyocyte showed that wonderful plateau. So let's follow, let's go back and follow. So here we said for neuronal cell, what we learnt about sodium followed by potassium, right? For cardiomyocytes, exactly it is like that only, sodium, but followed by a calcium, followed by a potassium, or these things happen simultaneously. I will come to that, how the calcium is playing the role. Okay. Now, when we say about calcium, what does that mean? So, if you look at that plateau for carefully for a minute in your brain map, if you look at that plateau is telling the cell is remaining depolarized for a prolonged period of time. For a prolonged period of time inside the cell, the charges are positive. Cell is experiencing a very prolonged positive profile. How that could happen? So, I told you that normally a cell is sitting at a negative potential with respect to outside. It is at minus 80 or minus 70 or even minus 40. So, from minus 80, minus 70, minus 40, when it shoots up to 0 and overshoots 0, it means inside it becomes positive. It becomes positive because of the influx of the sodium ions. That much is clear to you. Now, how it can hold on there? It can only hold on there. It can only hold on there. Mark this word and everything will be clear to you. It can only hold on there when there is some other cation, some other positively charged ion are continuously getting influx, and that cannot be sodium. Why that cannot be sodium? Because sodium entry, the gating of the sodium happens at a very narrow window, and it does not happen, the gating does not happen because these are voltage gated channels. You remember when I taught you, it is the voltage gating, and voltage gating only happens at the negative zone. Voltage gating does not happen when the cell membrane overshoots 0. It only and only happens at a negative, when we see that all or none minus, you remember minus 40 or something, that is where, or minus 30 somewhere, that is where those are getting activated. It will never get activated at a positive frame. At the positive scenario, there has to be some other ion. That ion is essentially calcium, but from where this calcium comes? Now, this calcium is regulated inside the cardiomyocyte by an organelle called sarcoplasmic reticulum. And sarcoplasmic reticulum, it's something like that. If you look at the cardiomyocytes, okay, so here is a nucleus. Okay, here you have this sarcoplasmic reticulum sitting. These are the SR. These sarcoplasmic reticulum, the best and easiest way you can visualize a sarcoplasmic reticulum is, all of you have seen Scotch-Brite. You squeeze the Scotch-Brite and you know all the soap and everything what is there while you are cleaning a vessels or utensils, it kind of squeeze out, it goes off. That's precisely a sarcoplasmic reticulum is. There are certain electrical activity which happens to them. It squeezes, it is a storehouse of calcium. It squeezes out the calcium ions, but it has a mechanism. It squeezes out the calcium ions and it takes it back immediately. So, it is something like this, what a sarcoplasmic reticulum does, like suddenly it has a calcium output and then it takes it back immediately. So, what it does for a brief impulse out here, there is calcium and then it is being pulled back by sarcoplasmic reticulum, by SR. By the way, calcium has to be regulated very, very tightly, otherwise it can become excitotoxic. It will lead to toxicity because of excess calcium. So, what I will do with this concept, I will close in here. In the next class, we will analyze this action potential again from the point of view of sarcoplasmic reticulum and what activates sarcoplasmic reticulum, and that will kind of complete the story of ryanodine receptors. And then what we will do, we will follow up on the ECG, EKG, and I will give you a PowerPoint presentation which will kind of clarify all your doubts. Okay, thank you.